So we're happy to have Nika continue her tutorial from yesterday. So this is going to be going into general sum games and general static interactions and collaborative interactions. And thanks, Nika.
Okay, thank you for being here. Can I just ask, is there anybody in the room today who didn't manage to catch any part of the previous day's tutorial that I gave? It's okay if you can confess. Okay, that's good to know. I just wanted to see how much of an overview I have to give. So since everybody was here, we can actually dive right in. But let me just set the stage anyway to sort of remember what we were talking about, because yesterday we dedicated almost all of the time actually to thinking about interactions with an adversary, and that meant that we talked about online learning, min-max optimization, kind of connections between them, and a little bit about what happens, like what is so brittle about adversarial interactions, and how we can sort of think it more socially realistic ways of thinking about adversaries. And then we saw how classical things you've learned from theory of machine learning still stays very relevant today to the needs of beyond worst case analysis in learning, to understanding games. And at the end, I also talked a little bit about computational aspects, but sort of in the interest of time, I didn't go into the details of it. So what I tried to do today is to actually have the remainder of the tutorial be essentially independent of that computational aspect. So just to be fair to you, because I didn't go through it, so don't worry, we're not going to go over it again, but you're also not going to really need to talk about computational aspects of the first part as much anymore. So what we're going to do today is think much more about general sum, as Vasily said, rather than thinking about sort of adversarial interaction, thinking about more general incentives and strategic structure. And then we're going to see something very specific, which is more about collaborative interactions. And then I'll highlight once we get to the end as to some of the connections that might have not been as obvious. I'll just repeat them so that we kind of can bring them back in our minds. Okay. If you have any questions at any point, feel free to stop me. I really enjoyed that yesterday. We were having a conversation, essentially. That was very enjoyable for me, but I think it also helped a lot of other people in the room actually follow along better. Cool. So let's start. Kind of in terms of the structure of this section of the tutorial, which is going to be essentially this full hour and maybe a little bit of the next hour. We're going to talk about general sum games, and then we're going to talk about some of the solution concepts in these general sum games, how you'd compute them, how you will learn about them, and also thinking about non-myopic behavior, which is something we haven't yet talked about at all, but we'll get there. Okay, so let's start with general sum games. And if you recall from yesterday, we talked about zero-sum games, and we said that zero-sum games were sort of the point of them were to capture our interactions with an adversary. So whenever we were gaining, they were losing, and vice versa. General sum games relax that assumption that my gain is your loss or your gain is my loss by saying that there are these more general aspects of how your utilities translate to mine. And you could think about them as more general strategic manipulations that are not necessarily malicious, but they're just type of interactions that somebody is just trying to optimize stuff in their own life, and it still affects us. So examples of this, we talked about a very little bit at the very beginning of yesterday's session, was in ride-sharing apps where drivers or even riders try to manipulate whether or not they're available for a ride, whether or not they're going to accept a ride at this moment, in the hope that immediately, soon after, like in the next 15 minutes, in the next half an hour, the next day, they're going to get better rates. Another example we very briefly again talked about that's good to bring back in your mind is admissions, hiring, lending, a lot of other search type problems where we're essentially looking at some available representation of a person, their CV, their any other information we have about them. and we're making decisions based on that, but the person has ability to change the CV, either changing the representation of it, or even maybe getting some qualification, doing some certificate courses. And again, they're not being malicious. They're not trying to mess up my learning algorithm. All they're trying to do is to actually get better deal out of the learning algorithm. And that's why this is more generally strategic rather than zero sum. Okay, so we're going to look at the same setup. The only difference is now that we're not making any assumption about zero sum, which means that we're going to be talking about general utilities U1 and U2. As before, if I use the capital of U1 and U2, it just means that I'm accounting for expectations. And because we don't have the zero sum assumption, we also don't have the min-max theorem. The min-max theorem, if you remember, one way to say it was that hey, it doesn't matter if you go first or last, it's all the same. And you're going to lose this very nice property. And what that means is that now it actually does matter who's going to go first. And an example of this is just remember that we're again going to work with these mixed strategies where each player is going to pick a strategy that is a distribution over actions. And let's look at such a matrix. It's no longer zero sum. So if you were to be player one, and I was interested in your Nash equilibrium, in a Nash equilibrium of this game, what now a Nash equilibrium would look like would say that, well, Nash equilibrium means that neither of the players can unilaterally improve their payoff by just changing their own strategy. And the interesting thing here is that this is actually quite simple to compute for this game because player one has a dominant strategy. What that means is that for every cell, if no matter what player two has played, player one would rather play up because it's getting more utility by playing up, regardless of what player two has done. So what this is saying is that, well, player one in any Nash equilibrium should be playing up. Now, what does the second player two, the player number two would do? Well, player number two knows that player number one has committed to this essentially because in any Nash equilibrium, you have to be here. So player number two says that, okay, but I'm going to gain more utility by actually going left. So this UL is going to be the only, the Nash equilibrium, which happens to also be pure in this game. Note that in this setting, player one is getting +1 utility. So Nash equilibria, you can think about it as some kind of a simultaneous play, right? We both go with P and Q, and this is the outcome we are going to get. Now, let's consider a setting where player one could actually verifiably commit to their strategy. What that looks like is that they actually pick a strategy and they somehow either shout it out. There's somebody who's holding them responsible. After they have shouted out their strategy, there's no way that they're going to change it. Maybe there's a contract, there's no way to back out. So now if player one could commit in a verifiable way, now what can happen is that let's say player one decided for whatever reason to commit to playing down. What would player two do? Player two is going to say, well, player one has already committed to being here. What I am going to do is to see what I'm going to gain. And I'm going to, I should have changed it slightly so that it would have been a little bit higher. So I'm going to actually play right because let's assume this was 1 plus a little bit. So I'm going to play right. And what happens here is that this is the outcome I'm going to see. And player one is actually getting more utility. So player one benefited from the ability to commit. This is what it means to go first and commit in a verifiable way. In fact, player one could have committed to a slightly different strategy, a mixed strategy, by saying that I'm going to go up almost half the time, and I'm going to go down the other half the time. And this is still good enough for the player two to be encouraged to take column number R. And what happens is that player number one is going to be able to get 2.5 utility, which is the best player number one can do if it were to commit to a mixed strategy. So what is this saying? This is saying that there is a different solution concept, which is not Nash, it's not min-max, it's not max-min. That is what you should be paying attention to. And this is called the Stackelberg solution concept. What Stackelberg optimal solution, and sometimes I also refer to it as Stackelberg Equilibrium, is that player one is going to take the position of a leader, and player two is going to take the position of a follower. Leader and followers are different. The leader has to commit to a mixed strategy P, and then the follower will best respond to this strategy that was announced. What is this best response? It's just the best action it's going to take, given that P has been committed to. Now, it's a Stackelberg optimal solution if the leader commits to the best mixed strategy, accounting for the fact that the follower is going to respond. This is going to be shown this way. Oh, this should be P. So this is called a mixed Stackelberg equilibrium. If I don't call it mixed, just assume it's mixed by default. So what we showed in the previous slide is that there are some games that Stackelberg equilibria for the first player has better payoff than any Nash equilibrium. In fact, what we can show is something very general, and this is also due to von Stengel and Zemir from previous slide, which is that in any general sum game, the Stackelberg equilibrium's payoff to the first player is at least weakly better than any Nash equilibrium.
That's a question.
Yeah.
Where there's some third party that pulls this play it out.
Actually, the way that people usually imagine it is that, yeah, maybe there's a contract or the environment itself is allowing for this.
So somebody's enforcing this.
Or the environment by itself is enforcing it. Yeah, either a third party or just the channel that's there is enforcing it. So let's say that what I do is that I actually play my chips and then I come back and then it gets realized.
I was thinking that even a digital information, and you're even thinking about a cryptographic way to enforce it, that this idea that they actually have to follow up is not so clear.
Yeah.
So if somebody has the last step, they don't advise.
Yeah. So I can give you 2 examples of this where this is being used in practice. I have slides about this, but maybe it's also a good place to say this. So one place that this is used, especially in the mixed Stackelberg concept, is for physical security, not for digital security. And the idea is that for physical security, sort of your commitment is something like almost like this petroling schedule that you have. And then criminals or whatever, people who are trying to abuse and get around the security features that you have installed are the ones who sort of know this commitment because they've seen it, and then they're trying to get around it. There's another example, which is for a slightly different notion of Stackelberg equilibrium. I'll give that in a minute. Yeah.
However, looking at the definition of Stackelberg, someone would say that, I don't want to say that it is easier, but now it's like singlet optimization. But I have just to find what the one is.
So let's see if that's a fair characterization or not. You're right that I can think about this function as just a function of P if I knew what the best response was. But to be fair, even in the min-max, you were doing the same thing. This is a generalization of min-max. So in fact, if this was a zero-sum game, the Stackelberg equilibrium payoff is the same as max-min, min-max, and Nash equilibrium payoff. So this is not actually getting around the fact that it's not making the problem just a simple maximization of the concave function. You're right that it's structured still. And we're going to see a little bit more about that structure.
So can I ask something? So I believe that please correct me if I'm wrong, like if I compute a Nash, that is a solution to the Stackelberg.
It's not the optimal solution.
Sure, but it is a solution, right? It is.
Yeah.
Right.
So why is it a solution? So Nash requires stability on both sides, right? So Nash requires that the follower best response and the leader also best responds to follower. Stackelberg's advantage is that it's actually relaxing the fact that the leader has to be best responder.
Right.
That's why exactly this result holds, because it's a relaxation of Nash. And we're going to see that kind of like, I think you were asking about computation, we're going to actually see this. The fact that now we are not really looking for a fixed point anymore is going to help us in terms of computation. But it's still a function of, it's still not a concave function that's easy to just maximize. Okay, so this is just, this is about mixed strategy Stackelberg equilibrium, optimal Stackelberg equilibrium. Now, there's also a notion of pure strategy solution concepts for Stackelberg, and it's exactly the same as before. The only thing here is that now the leader has to commit to a pure strategy, and it has to commit to the best pure strategy, knowing that the follower is going to best respond. So enforcing these actions are easier because there is nothing non-deterministic is happening in the environment. And one thing about this is that because this is about pureness, now it's unfair to compare a pure Stackelberg optimal solution to a mixed Nash equilibrium. In fact, if I were to commit it to compare to a pure Nash, it would have been fine, but pure Nash is not guaranteed to exist. So you will lose the nice characterization of this. But let me say that in most applications, when we actually talk about pure Stackelberg equilibrium, our environment is really, really structured in the sense that, in fact, you have sort of like convexity and concavity in the right ways, almost in an artificially right way, just so that you don't lose too much by talking about pure Stackelberg. This is not going to be the focus of my talk. I'll give some examples about it. But essentially, I'm going to treat it the same as I would a mixed strategy equilibrium, because whenever we work with it, it happens to have a lot of nice structures that we want anyway. Okay, so kind of like what you would think about such a result about Stackelberg equilibrium, what it's telling you is that commitment is actually good for you. In the sense that if you can go first and commit, it's much better to take that option rather than rely on something that's like a general Nash equilibrium. In terms of applications, I'm going to give you two applications. So this is the first one I was talking about, the notion of physical security. The idea is that in security games, sophisticated attackers target the weakest point of a system. And so what you want to do is that you're going to protect targets so that the targets that are higher value to you are not being attacked. Of course, what value you assign to a target is different than a value that an adversary might assign, and that's why this is not necessarily a zero-sum game. Here, the leader or the defender has a set of resources, X's, and it can choose how to assign resources to different targets. And usually, you actually want this to be random because you want it to be unpredictable a little bit. So you will decide that such and such police force is going to be actually looking at such and such street or such and such neighborhood with some random schedule of events. The attacker here, its strategy set is a set of targets. And U1 and U2 are essentially utilities that depend only on whether the resources that you had in X were assigned to protecting the target Y that was attacked. If it wasn't protected and it wasn't attacked, you're not going to get any utility from it. So this is an example of security games. It's actually something that the specific model of security games that I mentioned to you has been used a lot in practice for stopping actually poaching activities, for checking tickets on on trains and buses that in the LA area that you don't actually have to card in. You sit in the train and you have your ticket. Somebody has to come and check it. It's been used by Coast Guard, by a lot of different security agencies. The other example is the example of strategic classification. Strategic classification Here, the decisions are this. This is like thinking about, again, admissions, lending, hiring. The idea is that the decisions are based on some observable attributes, and people can actually change those attributes to some degree. The learner here is the leader who's trying to come up with a classifier such that when a distribution of followers respond to it, it's still a good classifier. Now, what does responding look like? Each follower has some initial representation, and they may have to pay a cost to change this a little bit. Maybe they're just changing the representation of their CV. Maybe they're taking some certificate courses. And then what U1 and U2 are capturing is either the accuracy of this hypothesis on the new representation versus the old representation. Maybe it's how much you encourage people to actually take certificate courses that are good for them rather than just manipulating their CVs. These are settings that we typically think about pure strategy, but as I said, it's even the pure strategy setting is highly structured in these settings. In particular here, pure strategy itself is like a parameterized classifier. And if you are working with parameterized like linear classifiers, you're already putting a lot of structure on your domain. So these are two examples of application domains. And next, I'm going to talk about how you would now compute these equilibriums, because there were already some questions about that.
Do you have like any story or a real world situation where it actually went like learning system and something so people manipulated so much that there was inefficiency and was obviously.
Yeah, so there are a lot of stories. There was an insurance company that was tracking, I think maybe your Fitbit or like the number of steps that people were taking to set insurance rates. So then there were all these like hamster wheels for your Fitbit that were sort of counting it up. And it was a very low cost manipulation. That's one example of this. But these have been used in a lot of different places. There are some entertaining stories about them. So that's an example of this, but maybe a more lighthearted story of that, but there are definitely darker ones as well.
And I
don't know if they were used by Fitbit. I think they definitely changed their approaches. I don't know if they actually use the type of robustness yet. Yeah, I have to think whether or not people have actually used this after they have figured out that they messed something up or not. I don't have a good example to give you right now. But this has been used a lot to actually identify situations where people are doing these types of manipulations, or where these types of manipulations are in particular bad for some equity or fairness aspects as well. Those are definitely, I would say there are still more scientific research rather than saying that some company changed their approaches using specifically strategic classification. At least I don't know of it, but they've definitely been used to analyze them.
So just one thing about how sequential you're doing this. This is still like at the same time you both go into something knowing that I'm going first.
No. So
I have to go first and shout it and then.
Yeah, or the history is enforcing it. I'll talk a little bit about this, but you have. So the best response is coming after your strategy is announced,
and
right?
this is played only once.
You can right now think about that this is being played only once. We're gonna come back and change that a little bit. But when we talk about Stackelberg, it's just a 2-round game. It's not an infinitely many rounds of game. And the idea is that if you know everything about U1 and U2, you can just do this computation, and this is telling you what's the best policy to commit to. And then you should never touch that policy. You just commit to it, and that's it, you're done. That's the best you could do. But then if you didn't know, then there are questions about, oh, what am I gonna do? It seems like I need to maybe tune my strategy, and is that going to mess up with all of this incentive structure? We'll talk about that sort of at the end of the section. Okay. Other questions? Yeah.
So just to be sure, the way that I would see it is the following. I aim to commit to publicly to a strategy. So I'm thinking first, given that, what is the best response of the other player when I would commit, and I will choose the best one will give me the best liquidity for me.
Yeah. Yeah, exactly. You sort of pre-compute in your head this best response function. So then you sort of choose the best action for yourself, accounting for the best response function. Okay, so sorry, I needed to change this to a presenter so that I can move between the slides more easily. Okay, so next we're going to talk about how you would compute Stackelberg equilibrium. And an important aspect of this is to actually look at that utility function. If you wanted to just parameterize it just by your actions, accounting for best response, what does this look like? Well, we need to compute this, right? This is the function that I only care about, essentially, if I knew this best response. Like the best response is computed this way, but I'm going to plug it in and I'm going to look at that U1. So you could think about it this way, but let me tell you that in most cases, this is not an advantage. This is not actually a simplification. Because if you look at this U1 of P as a function of just P, you're going to end up with non-convex, non-concave, non-Lipschitz functions that are so messy that you didn't actually gain anything. There are very rare situations, and I would say that partially like artificially curated sometimes to make them be almost Lipschitz and almost convex or concave. And there are some examples of this if you want to look at where in strategic classification, what kind of classifiers in real life actually have those properties. This paper has a really nice list of them. So generally, these functions are not very well behaved, but what you can see is that even if they might not be well behaved over their full domain, they still appear to have piecewise nice properties, and we can see them. Okay, so let's take a look at this again. So I want to compute a mixed Stackelberg optimal solution, and I'm in any finite game. So this is exactly what I need to compute. And there is this very general approach that says that actually this is like computing multiple linear programs. This is called the MultiLP approach. And the idea is that maybe this is complex if I just look at this function, but this best response function is going to take only y different values. Those are the columns in my game, actions of the adversary or actions of the follower. So let's fix each action and let's just look at my mixed strategies that would have been consistent with that best response. This is the set of strategies that are consistent with the best response. Now, what do I see? That set happens to be a polytope. It's a polytope because it's defined by these half spaces separating when my strategy, the follower strategy y is better than any other y prime. And remember that these capital letters are always linear functions. They're just telling you expectation of something. So you have two linear functions, you're thresholding them, and you're taking an intersection of them, which means that if I just look at what kind of strategies would lead to a follower taking a specific type of action, then I am looking at the polytopes. So once I compute the polytopes, then all I need to do is to find the best solution in every polytope and take the best out of all of them, right? It happens to be that not only these polytopes are linear, but the best thing that I'm trying to optimize, this U1 of P and Y, that is also a linear function. Again, it's a capital letter meaning expectation. So that I can optimize easily with a linear program. So what this is saying is that you just run a linear program per column of the game and then take the best one. And this is going to be your optimal Stackelberg equilibrium. How much time does it take? Well, it's going to be polynomial in the size of the game because I have to run an LP for each one. And the LP is in the dimension of my row space. Any questions about this?
Our flag can be a big strategy, like maybe two
Okay, so that's a good question. So I simplify this by talking about the player number 2 only playing pure strategies. And in general, it's okay to make this assumption because you assume that player 2 always can, for any non-deterministic strategy, there's a deterministic strategy that's getting just as much. So there's no reason to look beyond. But if they, so because of that, it doesn't actually affect it. The only thing that it affects is that it's actually changing the meaning of Stackelberg Equilibrium. And typically the people, like you might have a lot of Stackelberg, you might have, the best response is a set, not necessarily a single. Exactly, it's like it could be a set of columns rather than a single column. And you usually think about tie breaking in the worst or in the best case for the leader. And once you make whatever assumption you're making, you can adjust all of this. Let me tell you that it doesn't really matter. Essentially, what's happening is that you have these different regions is like P1, P2, P3. What happens is that, let's say that this is something that looks like this strategy that would have been optimal for one tie breaking. And as long as I move it a little bit in, it's approximately optimal, and it's out of the tie usually. So it's essentially you could really ignore these ties for now. In fact, for the duration of this tutorial, but they're interesting and you should take a look at them, especially when you want to think more about robust algorithms. So they come up again. Other questions?
Maybe I'm wrong, but I thought that these polygons have exponentially points, corners, so that the linear programming not be feasible to run.
Well, you can talk about the separation oracle because it's a polytope with y number of hypotheses, half spaces.
Right.
Then you don't have to think about the corners. You can just think about the separation. Other questions?
Just one question I would like to understand the following. Do we have right now assumption about the U1 if it is concave or not? If we're in the general assumption.
Okay. Remember, whenever we have capital letters here, they mean expectation. So we actually have linearity for them.
Okay.
Okay.
Yeah.
So that's the advantage of talking about mixed strategies and finite games.
You're right.
I don't need to make any additional assumption. Finite games by itself is a strong enough assumption to give me this. Okay. Okay. So this is also a minute to take a pause and realize and notice this, that this is much easier than Nash. That simple relaxation on one side, the fact that I don't have to find a fixed point, is making this essentially polynomial in the size of the game. Whereas we know in general, general sum Nash equilibrium is hard to compute. So not only this gives you a better utility to the leader, but also it actually allows the leader to compute it more effectively. Okay, what is an example of this multiple LP approach? I want us to maybe understand it a little bit better. I'm going to give an example from the security games, just so that you also maybe gain some appreciation of what security games and practice somewhat look like. So this is part of green security games. These are security games that are used to stop poaching or to limit it. And you can think about it that there are two types of potential targets you're trying to protect. You have elephants and gorillas. They're both close to extinction, so you want to protect them. And you have maybe sort of one resource that could be sent to one or the other. Now, these two targets are slightly different in terms of how you value them and how a follower values them. Elephants have ivory tusks, so they're very expensive. Attackers would love to get their hands on them. On the other hand, gorillas are closer to extinction. So you really don't want them to be attacked. So this is why it's not necessarily a general sum game. You also have two resources. One, it's a little bit of a oversimplification. You can decide which of these two areas you're going to send your resource. It turns out that what you would do in an optimal Stackelberg is to use almost 1/3 on the gorillas and almost 2/3 on the elephants. You do care about gorillas more, and the attackers care about them less. So you can get away with actually a little bit less protection than half and half. And that's why 1/3, 2/3 is optimal. Now, what does it look like in terms of the optimization? This is the space of the optimization. I should have drawn it on a line, but 2D simplex is a little bit easier to see. So any point here is a probability of how much you're protecting elephants and how much you're protecting the gorillas. And it's divided to two parts. How does the two parts are defined is that constraints on the followers' utilities. These are the lines. This line says that I prefer to attack the elephants over attacking gorillas. And they are written by the difference and by the comparison of the expected utility of the second player. Now, once you are within a region, you're looking at the objective, which is the leader's objective. Again, it's a linear function, it's the expectation. And now it's ignoring player number 2, it's just player number 1. So that's what linear program would look like. We take each of these regions, those are your P of Y's, and for each of them, it will optimize this linear function. Any questions about this? Yeah.
About the application, how do you decide who goes first?
Good. In all of these Stackelberg games, the idea is that the person who can set a policy is the person who's going first. So that's why protection policies, admission policies, those are usually long-term, and they're sort of verifiably somebody's sticking to them because they have put a lot of money or resources into making them happen. That's why there is a difference in power. So usually these rules are not inversible unless you actually don't have a hierarchy of power, which then messes things up. So a good point. I'll talk a little bit sort of towards the end, sort of algorithmic perspective on who's committing and who's not committing is itself an interesting way of viewing this. Okay, so here really one thing we don't want to forget is that we want to think about these general sum games, and especially a Stackelberg solution and commitment in them, because they're both easier and better. So whenever we can commit, we should really use that. Okay, we talked about computing these Stackelberg equilibria, but the computation needed us to know the game matrix. The question is, how much information do we actually need to know? And in realistic situations, do we have that information or not? Okay, so in the realistic situations, what is it typically that we do know? And what is it that we don't know? Well, for this specific scenario of general sum games, and let's think about security, I may know how much me as the leader values the different targets. I might know how close gorillas are to extinction. I might know how close elephants are to extinction. That's my half of the matrix, the U1. The thing that's harder to know is what is U2. Because even in the security games, even though I even know about the ivory tusk being valuable, it also really depends on what resources are available to the adversary and to the attackers and many other things, like where are they sleeping at night, how close they are to any of these targets. So that is U2, and I do not know U2. Sometimes you can do market research for certain things to figure this out, but usually it's quite sensitive. But the thing that we are hopefully able to observe, at least that's a simplifying assumption, is that even if you don't know U2, you can always observe what people have done. You can see what they've done in the past, what targets they've attacked, what targets they're going to attack right now. So that's the actual action of the follower. Now, what you're going to really be thinking about here is, if I'm trying to think about learning a Stackelberg optimal strategy, what I'm trying to do is to compute this function without actually knowing the PY. Because U1 I know, I just don't know the optimization region, because the optimization region was the thing that really required me knowing what U2 is. That's the polytope. So how can I do this? How can I optimize a linear function over an unknown polytope? That's the gist of the problem here, really. If you could do it, then you could do the multiple LP approach that I was recommending and put it all together. Any questions about this? So I wrote this in this very specific form of polytopes. There would have been many different ways of solving this, because the answer is essentially going to come out of this representation.
So can you do ellipsoid?
Can I do ellipsoid? So ellipsoid technically needs a separation oracle.
Can you get that from the other thing?
So that's a good question. So if I give you if I give you an oracle which is just about BR, can you get separation oracle? That's certainly something you could do. In fact, there's more generally, this thing is called a membership query. Let's say that for every, I have a polytope, I don't know its separation. I cannot, for any point, I cannot separate it. But if you put something in it, I can tell you whether it's in or out. If you put something out, I will tell you that it's out. So there are definitely ways to reconstruct separation from membership, but you can even do it more directly. Here, I'm actually going to cite, okay. I'm going to actually give you an example of a very nice work that actually covers all of the questions that you have. How can I go from one form of oracle to another? How can I optimize with a lower form of oracle? I'll do that in the next slide. But before I do that, I just wanted to tell you what this looks like, because I somewhat jumped a little bit to membership queries. So this BR, how am I going to use it? Essentially, I'm starting with not knowing anything. And BR is going to tell me that this is going to be in the elephant region. And at least this is going to tell me a little bit about the area. And what I have to do is to decide how I'm going to search the rest of this. You could think that it's almost like a binary search, but on a larger dimensional space. That's a little bit more complicated than that. In fact, you want one algorithm that can use this as simulated annealing. There are a bunch of other algorithms. It's independent, and we're not going to talk about it in the tutorial, but you can read about these. The optimization from membership oracles with membership queries is a well-studied, really interesting branch of optimization. We've known even before Kalayam 05, we have known algorithms for this problem, but the bound I gave you is from the 2018 paper. So we could do these quite effectively, actually. So now that we know how to solve an LP, we can put it back in the wrapper that I was suggesting to you and put it in the linear program formulation and just solve these problems. That's going to give you, for any finite game, an approach for learning the Stackelberg equilibrium. Now, the number of queries is going to depend polynomially on the number of the rows and number of the columns. There are other ways to do this. For certain games, you can do much better. I'm not going to go into the details of them. For security games in particular, you can do much better. For certain other games, you don't need to depend on the size of the game, but you can depend on certain structures in the game. There are also other approaches that can be used here. Yeah.
I always have to think of how this stuff gets implemented. Yeah.
Yeah.
So what? Where?
Sorry, I can't hear you.
Who's holding the oracle? Who's giving the response?
Okay, it's a good question because it's an oversimplification in its simplest form. So what I'm technically suggesting to you is to sacrifice the 5 Borlas that you have left. Because what am I saying? I'm saying you're going to start knowing nothing. You're going to start knowing nothing. And then you're going to actually at random put some point here. This is the point. And then you might see that actually this point is quite suboptimal, and maybe you even know and suspect that it's quite suboptimal. And then you see an elephant getting attacked. And then the next time you're like, okay, I'm going to move this. And the next time your gorilla is getting attacked. And technically, if you do this, before you can figure out a good strategy, your whole population of elephants and gorillas are dead. So this is not the way you should put this in practice. Nevertheless, this is actually used to inform practical decisions. It's not directly, the multiple LP approach I gave you is more of a scientific exercise. But these learnings, especially like slightly like safer ways of learning, is what you would do. Especially in sort of low value, like when to check tickets.
If I think about it cryptographically, if I think about there's all these equations, and I think of this as data rather than actual data.
Right.
Somebody's going to attack or not, but maybe more about the value of data, and depending on that, would they take an action? Then you could have some kind of maybe multi-party computation, or you could have committees and stuff. But without, you know what I'm saying? So there might be ways to.
I'm not sure if I caught that.
So you want to know what would have happened.
Yeah.
If you would have done certain actions. You have like perfect words of the future. You know. So if we're thinking about this all digital renewal interface, we can figure out what you know. So I'm thinking that cryptography is just a process, right? Where digital data like encrypted and some sort of computation under the what would have happened if you would that be like that?
So, but who are the parties? Are you asking the adversary to do some computation for you? Is that how I should think about that?
No, I think the way to think about it is that everybody commits. Okay. And given them committed, there is some way to compute what you want, like access and historical under. Now the only question is how do you get the answer? So
I'm not sure if I understand the role of crypto here.
I don't understand where you get, because you're saying you're going to make an action.
Yeah.
Then you're saying you're not going to make an action because then the monkeys or whatever they are, the gorillas are going to get attacked, if I understood. So you have to think of other ways to realize it.
I see.
You're saying that nonetheless, indeed, people have ways to realize it, and then they get these.
So the way I would fix this, I still have to think, I'm still not sure how I would think about the role of crypto, because this is, another way to think about this is that this is about lack of information, right?
So what I'm saying is this, I'm saying that instead of doing it, instead of taking actions and then seeing responses, you could sort of do a simulation of what would, if you would have done all these actions, what the solution would be.
That's definitely what you're trying to
What the
do. That's
response
true.
would have been without actually doing the action.
That's definitely true. So this is definitely an exercise. So this, like at a high level, falls under you've taken, let's say if you haven't taken any actions, then you are starting from no information set and you don't have much. But you have some observations usually, and that observation has brought it down to some set of uncertainty regions. And then you're trying to understand those uncertainty regions a little bit better. And thus you could sort of hallucinate a utility for the adversary and then best respond to that utility. I'm going to talk a little bit about online decisions, which actually do something like that. They're not, when you have to make these kind of fast decisions. Yeah.
I think that there are some theorems of photography that allow you to get things you don't imagine are possible. In other words, they do allow you to not just observable information and then it's partial information, but maybe it's much more without losing, without taking action. But they do release some information, which is what the Oracle query would have been. What the answer to the Oracle would have been had you. See what I'm saying? But
yeah, I mean, let me put what you said in a different way. I could have designed a game and I could have released it and asked a bunch of, I'm going to stereotype teenagers, sorry. I'm going to ask a bunch of teenagers to play this game for me. And then I'm going to look at the simulation that is produced by a bunch of people playing some kind of strategic game, especially if it was a pretty complex game, as an estimation of what my best response is. That's true. I can always have these other sources of best
Except
response.
you don't know the inputs that you're really gonna have in the game, because that.
I can create the inputs. That's okay, actually. What I don't know is whether or not people are actually, like, what is the utility of the people or how rational people are. So I can do these experiments to get an estimation of this best response, to have a warm start for my algorithm, and then come up with a very small set of these uncertainty sets, and then try those
It
out.
won't work, because in order to do crypto, I need to know what the response would have been given information.
Exactly. So the idea, I need to see this best response or an estimate of it. Now I can come up with different tricks to getting that estimate. But at the end of the day, it's about information that I need to see from whatever means possible. I saw a bunch of hands. I don't know the order. You want to go next?
Who goes first?
Who goes first? Comment. Go ahead.
I also want to inject something not crypto, but
Okay.
competitive analysis. So you're talking about a situation where your actions have some costs as you're going along.
Uh-huh.
And as you're trying to learn what actually to do. So why not add that into the model?
Good. I will.
You will. Okay.
I will talk about it in a little bit. It's not competitive analysis, it's regret, but
Yeah.
you can actually nicely go between regret. Well, you can go between regret and competitive analysis. 9 minutes. How about, are there questions?
No, I wanted just to answer that.
So maybe we can take that
Ask your
offline.
question. That's good.
Do you have a question?
Yeah, just so we're assuming here that U2 is fixed, right?
Good. I'm going to relax that too. Is that the question? Good. So you guys are all ahead. Let's go back to where we were. It's just the next slide. Okay. So okay. So I had made a simplifying assumption in some sense. It's not necessarily simplifying, but I assume that there is one type of follower, or and even if I don't know, it is somewhat fixed. And I had assumed that I'm spending all of this time coming up with a solution and then implementing that solution at the end. But you could have thought about this problem as one that is an online way of decision making. You have some system, you're making some decisions, and then you're going to tweak these decisions. And you can even think about having potentially different types of followers being presented to you that are they coming from some distribution, or they're coming adversarially from some set. So in a repeated game formulation, I could actually write this as something that we now call Stackelberg Regret. And Stackelberg Regret is very similar to the other notion of regret we talked about, in the sense that I am going to measure the leader's utility per round and average it out. But the thing I'm competing against is going to be the Stackelberg optimal strategy. Why is this a Stackelberg optimal strategy? First, note that this T I put here is exactly for what was the suggestion, which was if I'm dealing with a different follower, what would have happened? If I fix this follower, this is the definition of a Stackelberg optimal strategy. Now, if I don't fix it, it's essentially the Stackelberg optimal strategy for the sequence that I have observed. So this is what we call a Stackelberg regret. And if you have an algorithm that has low Stackelberg regret, what it now means is that maybe you were never close really to what you have to the strategy itself, but the utilities that you gathered around when at every time the follower somewhat myopically responded to you, best responded to you, would have not been very far from the Stackelberg equilibrium. That's how you would interpret this Stackelberg regret. And the idea is that actually the type of offline algorithms I told you, the search algorithms, that they spend a lot of time with membership query or whatnot, and then they learn something, they could all be turned into online algorithms that spend that time in one way or another in an online fashion. And either towards the end, they are comfortable enough to commit to something, or they continue sort of exploring and never necessarily committing. So there are these algorithms that are designed for Stackelberg regret. Many of them are actually inspired by the type of algorithm I already gave you, which spends some time searching and then commits. So
Is P-star adapted
It's this decided in hindsight. So I stop the sequence, I look back, and I define it. Okay, so now we have two notions of regret that we've been talking about. The Stackelberg, which I just introduced, and the regret we talked about yesterday. I'm going to refer to that external regret. That's another way of just another terminology for the same idea. And they're slightly different from each other. So if I were to think about external regret, forget about Stackelberg for a second. What it was saying was that you look back in hindsight, you see the observations, the actions that were taken, and you try to optimize for those actions. That is this type of maximization, in the sense that the observations were not at all a response to the optimal thing I'm doing. It's not about a policy. It's the actual observations that my algorithm, for whatever reason, the adversary had produced for it. Whereas Stackelberg regret, the benchmark has in it this type of a best response built into it. So they're different from each other. And they're different from each other in the sense that in the worst case, they're incompatible. What does that mean? It means that they're really optimizing for two different notions. If I get a Stackelberg no regret Stackelberg algorithm, and no Stackelberg regret algorithm, it's going to have regret, external regret on some sequences. And vice versa. If I get an algorithm that's guaranteed to be no external regret, it's going to have Stackelberg regret in some sequences. Why is this the case? It's essentially at the heart of it, partly, is that same difference I was telling you about min-max, max-min, Stackelberg, Nash, all of that. In some way, you're looking at utility in best hindsight on historical observations, versus utility on best responses. In fact, the advantage of Stackelberg optimal strategy was, as Kostas asked, was that the leader was not best responding. That relaxation was the thing that was allowing you to do better than other solution concepts. And the external regret is essentially telling you that you should be long-term best responding. Otherwise, you will have some regret. And that's why, in some sense, Stackelberg's solution must leave on the table, at least as it appears for the historical observations, something so that it appears not stable. It's not historically, it's not taking the full benefit of historical, full benefit of utility on historical observations. Also, on the other hand, external regret is not at all accounting for what this hypothetical of what would have happened if I did this or did that. It's just talking about the history rather than the type of history that would have been produced as part of your policy. And that's why these sort of. Okay, I'm going to start from here. And I know that break is coming soon, but I already see some questions. So how about we pause now? I'll take some questions and then we'll continue in 15 minutes. Does that sound good?
So are there any class of games in which we get all one regret for in terms of the external regret and secondary regret?
I can give
an understanding of that.
We don't have a characterization, but one class is zero-sum games. But I'm cheating because that's just easy. I'm not even sure if convex concave has that property. I don't know.
Just to be sure, phrase must appear, you mean should appear, it's not necessary.
It's not in every game, but in some game it must. That must happen in some game.
Okay. And just to follow up the question, do we have any information if that holds also for any convex concave?
No, I don't know. So like I haven't thought about this question before. If you ask me to give a class, I'll cheat by saying zero-sum games, but more reasonable answer I don't have right now. Other questions?
Could you say something about no Stackelberg regret algorithms, what they do?
Yes. Am I going to talk about them? Not really. Okay. So good. So let's go back to the example I was giving you with you spent some time doing the Stackelberg response. Now, one example of this is you could hallucinate a type of adversary. Or you might not even commit to a certain type of adversary, but like just kind of try to cover your bases for a bunch of different types of adversaries. So the fact that you will never again deterministically committing to any one type of query, you have a distribution over these queries that you're asking. That's something that looks like an online no Stackelberg type question. Another way to think about this is that many of these algorithms look at this as a function. They think about this function as just some function of P. It's just that function is not very nicely structured. And then what they have to do is to design ways to get information about this function while sort of covering their bases in terms of all possible ways that this function could have been written. I'll talk very briefly when we come back about bandits. I'm not going to go into the details of them, but that part hopefully is going to answer your question a little bit more. But because I didn't cover the computational aspects yesterday, I don't want to give actual algorithms right now. One more question?
Yeah. So what down? Stackelberg Regret?
For finite games, or you can get this the same thing I was telling you, as long as you limit the possible size of so you start with different possible followers, right? As long as you make that small, that set, you can get the same regret, but usually logarithmic in that size, or something that has some additional annoying dependencies on x and y's again. It's actually it's not that hard if I just limit the types of games to say that it's one of these k, I just don't know which one. I'm gonna get like poly in k, and then root t and everything else. But to do better than poly k, you need to use structures of the game better.
So let's take the rest of 9 and we'll have a 30-minute break.
Is it 30 or 15?
30.
Okay.
Oh,
Online it was 15.
yeah, sorry, yes, sorry, you're right, you're totally right, yes. So this is gonna be a 15-minute break.
Oh,
Yes, so because we're gonna have the town hall at 4:15, and at 5 we need to exit the room. So we have some time for the town hall, we're gonna have a 15-minute break this time.
Okay, I'll see you guys at 3:15. I finished on time. You guys ask questions.
We can start the town hall a few minutes later, it's fine, yeah. We
can do 3:20 if you want.
Yeah, 3:20, yeah,
Okay.
let's do like that, yeah. Yeah, let's take a 20-minute break.